This screencast is for AP Chemistry in Chapter 19. First law of thermodynamics talks about the conservation of energy, and that energy can be, it's not created or destroyed, but it is transferred from one situation to the next. Just like when we were learning in thermochemistry way back in honors, we talked about that the heat went from the system to the surroundings. So you knew that the energy was going from whatever reaction or whatever situation you're looking at into somewhere else. And we often use heat energy or just energy to run tools or lights or whatnot. So you're not losing it. You're just shifting where it is. It's transferring where it's located. So we have a new word we're going to look at. It's called spontaneous. So a reaction is spontaneous when it happens on its own without any outside help. So if you have an ice cube on a warm day, the spontaneous reaction is that it's going to melt. It is going to go from a solid to a liquid without any outside help. Now you might argue that the energy is being transferred from the sun to the ice cube, but really you just have it in a warm environment, and that reaction in the warm environment in the situation that it's at is that the ice cube will melt. Now you can have you cannot take, as you look at this picture, you cannot take an egg in the shell and automatically turn it into a cooked egg. Now if you add energy to it and it's in a warm environment, you could, but so you have to be careful of the situation. You need to be aware, though, that we cannot change the direction of this particular picture. We cannot say that the cooked egg is going to go back into the shell. So that reaction or that direction is not spontaneous. But the reaction where we take the egg that we crack out of the shell and we put it in a skillet and it cooks, that would be a spontaneous situation. Entropy is the concept of disorder. So it is abbreviated with a letter S, and we're going to spend a good portion of this chapter solving for entropy. Entropy is talking about the amount of order in a reaction or in a situation. So if you're looking at two gases and they react to form three, you would say that you're going from a situation where you have two molecules to three molecules. That is more disorder because three things can move about with much more freedom than the two things. The example that I'm showing you here in the pictures, you have a clean teacher's desk, and then you have a not so clean desk. I'm going to go with that's a teacher's desk. Look at all those papers back there. You can see that if we are going from this particular situation where it's clean and we're going towards the mess, the disorder is bigger. It is much more disordered. So we would say that this S is positive. This delta S is positive. It has a much more disordered occurrence or appearance. And that is a spontaneous reaction. If you think about it, anything in nature, if it's organized to start with, it is not going to become more organized. It takes energy to become organized. It is not needing as much energy to become disorganized. So if you were to say that the opposite direction, where we go from from the messy desk to the clean desk, that would be a delta S that is negative. And that is not spontaneous. It does not happen on its own. You need to put extra heat or energy into it. Okay, and we are going to solve delta S based on the heat, or Q, and the temperature. So we're going to spend the next several slides looking at how to solve for entropy. I will say that entropy has values in the appendix in the back of the book, and they are measured in joules. All right, so we started with the first law of thermodynamics, and this is now the second law of thermodynamics. And the second law says that entropy will increase or stay constant. Okay, so typically the reaction wants to go towards more disorder or hold its own. It's not going to go better. That takes energy. That's not a spontaneous reaction. So gases will expand spontaneously. If you spray perfume or you put lotion on your hands in one particular portion of your room, eventually you're going to smell the lotion or the fragrance in other places in the room or even the house. The same thing happens here. I have a picture of the pizza. If somebody walks into the front portion of a room or a house with a hot pizza that has a lovely smell that everybody enjoys the smell of pizza maybe, eventually the rest of the house is going to know that the pizza was here. Or you can go with it as a stinky kinds of thing. Maybe it's somebody has a stinky cheese, and everybody's going to know about that stinky cheese as the gas molecules are moving around the room. They're no longer just staying right beside the pizza or the cheese. They're bouncing around, hitting each other, and they're spreading out. Molecules will spread out to become more disordered. So instead of having all your little pizza molecules hanging out just in this lower corner, it's going to fill the whole space. So anytime that you have a process where the disorder increases, remember it's spontaneous. So let's look at these options here. So which of these is less organized or, has a higher entropy? You have a solid, which has particles that are fixed, or you have liquid, where the particles are moving around in the portion that is the liquid. So the less organized would be the liquid. If you're looking at the liquid or the gas, liquid is contained and has a finite volume. A gas has no finite volume. So the gas would be the one that has less organization or more entropy. And then 3 moles or 10 moles. I often use the example of if you have to watch 3 kindergartners or 10 kindergartners, which is going to make more of a disaster? And the answer is the 10. The same thing could be said of, molecules or moles or atoms. The more that you have, the more disorder you can potentially have. All right, here's a sample problem where mercury is a liquid at room temperature. Normal freezing point is negative 38.9 degrees Celsius. Its molar heat of fusion is 2.331 kilojoules per mole. Fusion means melting. That's down here on the bottom. It says, what is the entropy change when 50 grams of mercury liquid freezes at a normal freezing point? Okay, so what we need to do first is that we're going to remember that because fusion is melting and melting is positive, so that means that freezing is going to be negative. So we're going to change our 2.331 into negative because it is freezing. Okay. We're going to also take and find the number of moles of mercury. So 201 grams per mole. I got that off the periodic table for mercury. So our value is 0.025 moles of mercury. Okay. To find the Q, we are going to take the delta H times the number of moles. So Q is our delta H times our moles. I got our moles here. And we have negative 2.331. So that value is 0.583 kilojoules, and it's negative. Okay. So if we wanted to find our Q in joules, it's going to be 583 joules, negative. And so our delta S is we're going to take the Q divided by the temperature. So we have our negative 583 joules divided by our temperature in Kelvin, 234 Kelvin. And our answer is negative 2.48 joules per Kelvin. So because this is negative, we know that this reaction is not spontaneous.